Yeah.
Hello, everybody.
Hello.
Hello.
Hi.
We were just talking about your email.
Oh, that's okay.
Oh yeah, I did that in the past.
Dear. All right, so it looks like we're just doing cyclohexanes today, or cycloalkanes. Okay. All right, I'm going to play a bit of the video here, but not, well, I'm not really going to play it per se. I'm just going to show bits and pieces from it. Let's have a look. I know you can't hear it, but that's okay. All right, you can all see my screen though, right?
Yes.
Okay. So we're going to look at some of these cycloalkanes here, and we'll look at cyclopropane first, and you can see that when you view it from the side, because of the way that it's shaped, it's very difficult for the hydrogens not to be eclipsed. So I think I actually show that. So you can see everything gets eclipsed. So cyclopropane is very unstable. The other reason it's unstable is because it's got 60-degree bond angles, and because they're single bonded, it really wants to be 109.5 degrees, which would be sp3 hybridized. Now, how do I know it's 60 degrees? Well, it's a triangle, and it's an equilateral triangle, which means that all the angles are equal, and everything in a triangle adds up to 180 degrees. So there are each 60-degree bond angles, which means it's very strained. Cyclobutane, likewise, is also quite strained as well. And you can see there the cyclobutane will actually twist a little bit out of the plane like that in order to make the hydrogens less eclipsed, but they still end up being pretty eclipsed, so that's pretty unstable as well. Now the next one, the cyclopentane, that one can shift itself pretty much out of the plane and make it so that the hydrogens aren't eclipsed. The other thing with cyclobutane's 90-degree bond angles, obviously, since it's a square. Cyclopentane, we're a lot closer to 109.5. I think it's 108 degrees. The internal angles of a pentagon, but it's not really a pentagon per se because it twists itself out of the plane and it ends up looking more like an envelope. So you can see it kind of looks like that shape. But what happens is that these carbons sort of rotate around and nothing ends up ever being eclipsed for very long. Cyclohexane is even better for this. And when it sort of looks more like a chair. That's why it's called a chair conformation. Like a sofa, looks like a sofa. Lazy boy, I should call it lazy boy conformation. And you can see in the chair conformation, none of the hydrogens are eclipsed, which makes that pretty stable. Now, what we're going to be looking at is a situation where we can see the two chair conformations being formed, and I'll show you how that goes in a second. I'd encourage you to watch that mini lecture, by the way. I was just giving you some of the highlights here.
Can I ask a question?
Yeah.
Why two? Why is it going from one chair to two chairs? What is?
Well, I'll show you that right now. Okay, so this is a typical chair conformation. This is what it looks like. See, the black balls here are carbon atoms, and then the red and blue balls here are hydrogens. Now, we've got two flavors of hydrogen here. We've got hydrogens that are blue. Those are the ones that are pointing up and down. We call them axial. So think about the Earth's axis, how it goes straight down through the Earth. So these would be parallel to the axis. The red ones here are called equatorials because, well, they'd be around the equator. So if you think of where the equator is, and these are the ones. Now, keep in mind that they do alternate. The axial ones, they go up, down, down, up, down, up, down, up. And the equatorials also alternate. This one's a little bit up, this one's a little bit down, a little bit up, a little bit down, a little bit up, a little bit down. And it takes on this shape here because that's the lowest energy possibility for it, that has all the hydrogens not eclipsed. So let's take a look at what the interconversion looks like. And Julie, this will answer your question as to why we're getting two of them. In fact, I'm going to stop the share here and I'll create a new share. And we'll share the computer sound. Here we go. All right.
Got this movie that I've taken from YouTube. And what we'll do is we'll play this, we'll play it in full screen. Now before we get started with it, let me make a couple of things clear. Look at the blue sticking up and down equatorials, because this one's a little bit down, this one's a little bit up. There's the interconversion itself. And what happens is that it turns into...
All right, so you can see that it turns into this boat situation first.
To what we call a boat form. And then it twists. And we get our other conformation, which now has the reds axial.
So now you can see what was axial is now equatorial, and what was equatorial is now axial. So that's a shift. It's different. It's different to what it used to be. See, this carbon used to be, I'll show you where it was. If this is, I'm pointing at this one here. I hope you can see my cursor. Look where it used to be. It was pointing interconversion. See, it was pointing downwards like that. It was down here. And then when we twist it, this one twists upwards and this one twists downwards.
Equatorial. Boat again. Blue's axial, red's equatorial again. Now what I want you to do.
So that's how it interconverts. And that's a good video because it shows you where the interconversion's going and what it's doing with the hydrogens. Julie, does that answer your question?
No, because I don't understand what, okay, I guess it's hard to ask this question. I see this and it's supposed to be like a chair in one direction and then a chair in another direction.
Right.
And what you said before about cyclohexane being a chair, it didn't change between then and here. It's just, you're just saying it's chair because it's moving. Is that what you're saying?
Yeah, well, we're twisting this C at the end upwards and twisting this C at the end downwards, which changes or interchanges the hydrogens from axial to equatorial and equatorial to axial.
Okay.
So they are different.
Okay. I'm willing to accept that.
What's that?
I said I'm willing to accept it. I'm just not sure why it was a chair before and it's two chairs now.
Well, it's still, I mean, no, it was a chair before, it's still a chair. That's all.
Thank you.
I have a quick question.
Yeah.
So in transition from chair, then it goes to boat.
Yep.
To the, it switches, the axial switch. So the middle transition would be boat.
Yes. Yeah. But we're not interested in the boat. The boat's a very high energy conformation.
All right, that's what I was wondering. Thank you.
Yeah. The boat has pretty much everything eclipsed. So it's not a form that it will stay in very long. Yeah, that's pretty much all I wanted to show you with that.
Is it moving continuously, or is it
Yes.
staying longer in the other positions where it's more comfortable?
Well, it sort of stays in the chair positions a little bit longer, but it's always moving.
Okay.
Are these the only, I guess the only shapes that the molecule will take just between those three?
No, there's a half chair, and there's all sorts of different ones that lie in between. In that video, it goes into each of them, but we're really only focused on the low energy conformations, which are the chairs.
Gotcha, thanks.
At each end. But yeah, it does go into a lot more as a half chair, half boat, twist chair, a whole lot of other things that go on. But those are the chairs are the ones we're most interested in. Okay, all right. So let's talk about how we might draw these wonderful chair conformations ourselves. Oh, you didn't think you were going to get to do this, did you? See, I know you were heartbroken initially, saying, "Oh gosh, we're never going to get to draw these," but you will. You will. Okay, let's see what a chair conformation looks like. Now, this is how I like to do it. I kind of like to draw a zigzag that looks like this. And then I draw another zigzag behind it like that. And you can see that I've drawn it so that these two here, the second lines on each case, are parallel. So we end up getting something that looks like a lightning bolt. So this is going to be one chair conformation. The one that has the left C sticking upwards, if you will. That's this one right here that I'm pointing to. So I'm going to star it just for kicks. That's a star, by the way. It's not a very good star, is it? That's a better star. A little bit better. There we go. Now we can put on our hydrogens, and I always like to put on the axials first because they're easiest. And the best one to put on first is going to be this one here. I'm going to get rid of that star, it's in the wrong place. Put it over here. Is to draw the first axial on the one that's puckered upwards like that. And then alternate them. And there's all your axial bonds in there. And you'll see that they go up, down, all the way around. And it's really important to make sure that you don't do this. Now I'm going to show you this, but I'm going to erase it straight away after I do it. And that would be to do this. And the reason that that's wrong is because the bond angles would be completely wrong. Those bond angles wouldn't make any sense. So don't do that. Make sure that you start on the puckered end going up, and do it upwards. Whoops.
So the up end goes up and the down end goes down.
It does. That's a good observation. Now there's your axials. Now let's look at your equatorials. Now here's the thing with the equatorials. If your axial is pointing upwards, the equatorial is always going to point in the opposite direction, but out a little bit, not straight down. So this axial goes up, which means the equatorial goes down a little bit. This axial goes goes down, which makes the equatorial go up a little bit. And those alternate as well. Now, it doesn't matter which way you point the equatorials, whether you point them to the left or the right, but they do have to be in the opposite orientation to whatever axial one is on the same carbon. Hopefully that makes sense.
How would you draw a cyclic molecule with an odd number of carbons?
We're not talking about those. We're just talking about cyclohexane.
Okay, so we're only going to do this with hexanes.
Yeah, because
Okay.
they have that kind of special stability, but they can do this chair into conversion.
Hmm. But like the cyclopentane can also do stuff like this, right?
It can, but it's more the cyclopentane. It's more like one of them is kind of just moving around the ring really fast. It's rotating kind of.
Hmm.
So it's more like a rotational kind of set of conformers rather than two extremes like it is with the chair.
Does it matter if the equatorial lines go to the right or the left?
No. But
Okay.
it does matter that they're opposite to the axials on the same carbons, Julie.
Okay.
You know what I mean? They have to be pointing down if the
Yeah.
axial is pointing up, or up if the axial is pointing down.
Okay.
Okay.
On that note, on the
Yeah.
bottom left carbon and the top right, I might have drawn the equatorial hydrogens a little bit more towards 10 o'clock on the bottom and like into the interior of it.
That's okay.
Okay.
As long as they are pointing in the opposite direction to what the
When I'm
what
looking at the
axials
other
are.
two corners, I'm seeing one coming to the inside of the conformation and one
It
coming to
doesn't-
the outside.
It doesn't matter.
Okay, just different than the other
Yeah.
direction.
Yeah.
Okay, thank you.
So I'm trying to use my different colors here. Okay. Let's go back to blue. There he is. Okay, let's look at the chair. This is not resonance, by the way. This is actually an equilibrium. I missed one, didn't I? Put him on here. There we go. So what we do to draw the opposite one is the one I've got starred is now going to point downwards. So we do the lightning bolt again. It's not a very good lightning bolt. That is. All right. And you can see that the one I'm pointing to here with the cursor was pointing up, now it's pointing down, and this one here that's pointing down is now pointing up. Anybody got any questions?
I don't know about anybody else, but I couldn't see the cursor.
You couldn't see the cursor. I'll point at it. This carbon here is pointing, is now up, is now going to be down here. And this one, you can see the arrows though, right?
Yes.
Yeah. Okay. So those are the carbons I'm talking about. They're now in opposite direction to what they were previously. Now, whatever was equatorial is now going to be axial. And I'm going to put the axials in first. I'll do what I did previously. Do the one that's puckered upwards first. Alternate all the way around. Now, these are all going to be pink. So my point here is that whatever was equatorial is now axial. But here's what's really important here. You'll notice that if it was equatorial sticking up, it's still axial sticking up. And if it was equatorial sticking down, it's now axial sticking down. So they're not changing their orientation on the ring per se. They're just changing their position from axial to equatorial or vice versa. All right, so I'll put in the...
So it's kind of like the carbons are turning, but the hydrogens are staying put?
No, the hydrogens are also, well, the hydrogens are just changing position, Julie.
But
So
there's
it's like flipping a pancake.
I'm sorry, I didn't get that.
Go ahead.
So is it like flipping a pancake? Like it's on one side, and then you flip it over, and it's like the back side you're looking at?
Not really. No, it's not like flipping a pancake, because we are actually moving the bonds around. It's just like in that video. We are actually physically moving those bonds around. It's not like just flipping it over.
But the H's are staying in the same position as they are in comparison to the carbons than they were before, it seems like. It seems like just the inside is flipping.
No, I disagree with that, Julie, because when you look at this pink hydrogen that I'm circling here, right? I'm circling that one. It's now equatorial in this conformation, but then in the second conformation, it's now axial. So the hydrogens are moving.
So will axials always be the straight up and down ones, and the equatorial will be more left, right?
Yes.
Okay.
Yeah. So that's what I'm trying to do here, is I'm trying to say that the red ones here, initially, H is axial here, and here the red H is equatorial, and in the pink, the H's were equatorial here, now the H's are axial in this conformation. That's what I'm trying to say. But the reason it moves, the reason it happens at all is because this carbon is being twisted downwards and this carbon is being twisted upwards. And of course, you know, it goes both ways. I mean, this will go down and then this one will go up to come back to the other one. But that's the nature of the interconversion. All right, does anybody have any questions? All right, let's look at what happens if we put a different sized group on there. And this is Methylcyclohexane. So what we've done here is replace one of these hydrogens with a methyl group. Now, in so doing, what happens is that the methyl group in one conformation changes from being equatorial into being axial. So just doing this one again. By the way, it doesn't matter which one of these you start with. I'm not going to do different colors for this one. So that's one conformation. Does it matter where the methyl group goes? No, it doesn't. In fact, I've actually got this opposite to the way I've got it on the thing, but it's okay. I'll put the methyl group down here and put hydrogens here.
So we can just write CH3 and be fine. We don't need to write all the hydrogens off of it.
No.
Okay.
No, we're only interested really in what's connected to the ring here. The other hydrogens are important though. Now, so you'll notice here the methyl group is axial. So when we do the, excuse me, the opposite one. You'll notice what happens is that, again, I'll put in my axials. you'll notice now the methyl group has shifted into the equatorial position.
It has to be the one next to it, right?
Well, that's the star carbon there, and that's the same star carbon there.
Okay.
And then the rest of the hydrogens go on. But the point I'm trying to make again is the same point as I made earlier, is that that methyl group is sticking down on the top one. It's still sticking down once it becomes equatorial as well. But when I say down, I mean relative to the plane of the ring. If you think of my hand as being the plane of the ring, the methyl is sticking downwards. It's either going to be axial or equatorial, but sticking downwards.
The way it's drawn in the notes, it's a little hard to see.
I know,
that
I know.
axial.
Well, I know it's the. You mean?
So it'd just be the comparison of the two.
You see, it's a bit. It's opposite here. You'll see, I drew the. It didn't.
I do.
Yeah, it's opposite.
But I mean, on the left side where the methyl group is axial, the way it's coming down.
Yeah.
Not on that side, on the left side.
Yeah. You mean over here?
It's a little harder for me to see that it's axial if I didn't have the second group to compare it to.
Well, this isn't, the one on the left isn't axial, it's equatorial, the methyl group.
I'm sorry, equatorial, that's what I meant to say.
Oh,
yes.
okay.
But I'm saying it's a little hard for me to see it because it is pointing down at an angle from the
right,
but
the axials always point directly up or directly down.
But what about the equatorials?
Well, they're going
That's
to
what I
point.
meant to ask about.
Well, they're going to point in the opposite direction to be axial, but just a little bit out.
Okay.
But not directly.
So there's not
down.
going to. It's not exactly perpendicular. There's a little bit of variation for the equatorials.
That's right.
Okay. That's
well,
what
the equatorials are perpendicular. I mean, they are pointing upwards directly, but the bond angles here are 109.5 between. I know you can't see the cursor, between the H and the CH3 on the same carbon.
That's why it's not 90 degrees.
Right, it's not 90. That's exactly right. Yes, it's not 90.
So you really, when you're drawing them, you want them a little bit more at 109.
Yeah, that's right.
Okay, that makes sense.
As opposed to 90, yeah.
Okay.
Now the issue that we face with the methyls, and you can see it over here in the slide, is that the axial methyl is actually more unstable than the equatorial methyl. And the reason for that is because the axial methyl interacts with these two hydrogens that are, you can see these lines here. I know you can't see my cursor. I'll see if I can draw it on this one here.
That we can't see the cursor.
I'm sorry, what's that?
We can on the I can on the PowerPoint.
Oh,
it's a drawing board that I can't see it.
Oh, okay, fair enough. Oh, good. Then I'll point at it here. So this hydrogen here and this hydrogen here are flagpole hydrogens, they're called, and those interact with the hydrogens that are on the axial methyl group, but they don't interact with the hydrogens that are on the equatorial methyl group. And what that means is that the bottom line is that the large groups, and when I say large, anything bigger than a hydrogen, is always going to want to be equatorial or would prefer to be equatorial. Now, I'm not saying that the axial one doesn't form, it does. It's just that maybe this is in a gas phase, you would probably get maybe 75% of the equatorial and 25% of the axial if you were to take a snapshot of it at any given point. So the equilibrium would be more on the equatorial methyl side rather than the axial one because it's lower energy, more stable. So lower energy means more stable. Higher energy means less stable. Does anybody have any questions? Okay, so on the test, you'll be given a dimethylcyclohexane. And there are 6 possible ones that you could get. And it's going to be definitely one of these 6. So it could be cis 1,2, trans 1,2, cis 1,3, trans 1,3, or cis 1,4, trans 1,4. So that's it. Those are the 6 possibilities that we can have. So I'm showing you here cis 1,3. And I'm going to show you how you would draw these chair conformations for that. So this is, it doesn't matter which one we start with. And it really doesn't matter where you put the methyl groups either on which carbons, but 1 and 3 means that it goes 1 to 3. So 1, 2, 3. 1, 2, 3. And I'm just going to stick the methyl groups downwards here. Now they do have to go in the same direction. If it's cis means that they are both going to be, in this case, pointing down. Now, one thing I want you to realize, and this is a point of confusion that I often see, is that cis doesn't mean both axial or both equatorial, because I can show you examples where it's going to be cis. In fact, I'll do one over here. This will be 1, 2. This will be cis. So this is 1, 3. Cis 1, 3. This will be cis 1, 2 that I'm showing you here. So the methyl group sticks down, and the other methyl group also sticks down, but it's going to be equatorial. So in this case, they're both axials in cis 1, 3, but in cis 1, 2, one would be axial and one would be equatorial. How do I know that? Because if I draw in all the axials and equatorial, you see the axials will be alternating. Same with this one here. I'll just go ahead and draw in the axials and then the equatorials. All right.
On the test, would we need to draw in all the hydrogens?
Yeah, you do. It's not really technically a line structure, it's a chair conformation. But we need to draw in the hydrogen so we can distinguish between where we have things.
How do you know they're both pointing down?
Because it says cis.
So if one points down, the other has to point down.
Right, if it's cis. If it was trans, one would be up, one would be down. So this
Maybe
is
sorry, go ahead.
This is what trans 1, 2 would look like. I won't bother putting in the hydrogens here, but that one's down, this one would be up. So that would be trans 1, 2. Okay, so you had a question?
Yeah, maybe it's just because part of the question's covered up, but how did you know to put them on 1, 3 and 1, 2?
Oh, no, these are 2 separate examples. This example I'm doing is, I'm just following along on the PowerPoint, which is 1, 3. But I wanted to make a point that if it was cis 1, 2, they'd both be sticking down, but they both wouldn't be, cis doesn't mean both axial or both equatorial, is the point I was trying to make.
And it doesn't matter if you choose up or down for the cis?
No, as long as they're both pointing in the same direction. But I'll delete this now just because I don't want it to be a confusion anymore. Now, if I had have done it with them both sticking up, they would have been both equatorial, which would have been fine, by the way. Okay, let's look at what this looks like in its second form. So we do our axials again.
Can I ask one more question?
Uh-huh.
You said they'd both be both equatorial. That's assuming that one is on the right side, but what if you used one on the left side?
It wouldn't matter. It'll still be the same.
I don't understand why.
Because this is 1. This will be 2. That'll be 3. This is also 2, and that's also 3 there. Is that what you're pointing? Is that what you mean, Julie?
No, what if the other side was 1? All the way to the other side.
Okay, then what would happen is that they would both be equatorial then.
They couldn't both be axial? I don't understand why.
Well, it doesn't really matter where you put the methyls as long as you put them both pointing in the same direction, because it's supposed to be cis. You have to be both pointing down or both pointing up.
So okay, but you said that they would be, equatorial.
If they're on the same carbon, Julie, if they're on the same carbons and pointing upwards, that would still be cis, but they'd both be equatorial.
Okay.
So what I'm saying is they'd be where these circled hydrogens are. They'd switch places.
Oh, assuming they're on the same carbons. Okay.
Yes, yeah. All right, so let's go with what we'd see on the. Now this one carbon is star 1 is the same carbon here, and this methyl group would now be equatorial on the same carbon, and then this methyl group over here would now be equatorial. But notice that they're still both sticking down. So someone had made the comment about it being like a pancake. No, it's not really, it's not like a pancake at all, because the methyl groups are just changing position due to the orientation of the bonds being changed. So what we're doing is shifting this carbon up and shifting this one down. So then we put on all the hydrogens here. Now, the other part of this question would be, which one of these would be more stable or the favored conformation? And the answer to that is neither. Oh, sorry, no, I'm lying. The answer to this one would be this one, because we've got 2 equatorial large groups versus 2 axial ones. And as we talked about, the axial ones are less stable because of this interaction between the axial methyl group and the hydrogens on the ring that the equatorial doesn't have. So both large groups are equatorial. So let me show you what, let's see, oops, wrong one, here we go. All right. So I actually have this in the blue book as well, these pages, and you're going to get one of these 6 on the test. Could be any of them, but it's going to be one of them. So you'll notice that in the case of cis 1, 2, they're both sticking up, but one is cis and one is, sorry, one is axial, one is equatorial. And in the case of cis 1, 3, they're both axial and both equatorial. But you'll also notice that in situations where one is axial and one is equatorial, neither are favored because they both have the same energy. So the only ones, so it's going to be 3 that have a favored one and 3 that don't. So I'd recommend just practicing each of those 6, and you'll be fine.
Can I ask you a question?
Yeah.
I'm sorry. I got confused. If the favored ones are if they're both equatorial.
Yeah, and
but if they're one's equatorial and one's axial, then there's no favoritism.
That's right.
Okay.
Because if it's one axial, one equatorial in one, it'll be one axial, one equatorial in the other. And if it's both axial in one, it will be both equatorial in the other, and vice versa. But this page shows every single last one of those examples. All right, does anybody have any questions? So it's a matter of practice. You've got the videos there. That's helpful because in the videos I go through how to draw them, putting in the axial hydrogens, putting in the equatorial hydrogens, showing the equatorial groups, the axial groups. I have a couple of examples of these in the video too. All right, does anybody have any questions? All right, let's see. I know I had only wanted to cover the chairs today, I think, but I think I want to get into the stereochemistry since we do have the time to start it. I think I will start it. Just the introduction part. But let's take a look at what the test question looks like. Oops, wrong one. So as I promised, I did add 2 more old tests to these.
Thank you.
But we're looking at question 4 here. Draw chair conformations of trans 1,4-dimethylcyclohexane is one conformation favored. All right, so let's take a look at that. So we're looking at, I think I said trans 1,4, right? Sorry. Yeah, trans 1,4. Now, it doesn't matter which one you start with, which lightning bolt, but put the axials in first. You'll notice I started here at the one that was puckered upwards, and then put your equatorials in.
What was the name of the molecule again?
Trans 1,4. I'll write it up here.
Dimethyl.
Yeah, they're always going to be dimethyl, right? Always. So I'm just writing trans 1,4 here.
That makes it easy.
Yeah. So there's your first one with all the bonds drawn in. Then we put the methyl groups in. Now it doesn't really matter where you put the methyl groups. They just have to be, well, they have to be trans. They have to be on the first and then the 4th one around from it. I prefer to put a methyl group on one of the ones that's puckered up or puckered down because I think it makes it easier. But I'm going to go ahead and stick a methyl group here on this one on the first one, the one that's puckered up, and then I'm going to move around 1, 2, 3, 4. I'm just going to point at this because I know you can't see my cursor, but that would be the 4th carbon around. Is everybody okay with this so far? Now it has to be trans, and trans simply means one has to be up and one has to be down. Now that methyl group on this end here that's circled is pointing upwards, and the one on the arrow that points downwards would be this one. So there's your trans 1,4 there. Does anybody have any questions? So after that, go ahead and put the hydrogens on. And then draw the opposite lightning bolt. Go ahead and stick your axials on first, starting at the one that's puckered upwards. and stick your equatorials. And the one that's circled here, I'll circle down on the other one as well. And you can see it's moved down to be puckered downwards. The methyl group was axial, it's now equatorial down here on the second one. And the other methyl group is also equatorial. And then we stick in our hydrogens here. So it's really important to note that the methyl groups don't flip to being the opposite direction to what they were. They're always, if it's pointing up, it's still going to be pointing up. If it's pointing down, it's still going to be pointing down. They're just going to be in the opposite direction. So for this one, since we do have two axials over here, then this one is favored because both large groups are equatorial. That's how you do it. Does anybody have any questions?
Is that the only explanation we'll need for the answer?
Mm-hmm.
Can I ask you a question?
Mm-hmm.
Is it safe to say that cis 1,3 will be the only cis that has favorites and trans 1,4 and 1,2 will be the only trans that have favorites?
Yeah, that's probably right, because I know it's 3 and 3. I know 3 of them do, 3 of them don't. Because there's a total of 6, Julie.
Right, so, because it depends on, obviously, if it's every other one or every right next to each other.
That's exactly right. And whether it's cis or trans, of course.
Well, because that's affected by it, yeah.
You're right.
I get
Yes,
it.
but going back to what you're asking, I mean, you can look through the list here. You can look through the list here, Julie, and you can see which ones are going to be favored, which ones aren't. So the ones that have yes, cis 1,3, trans 1,2, and trans 1,4.
4. Yeah.
Okay, and the other ones don't have one that's favored.
Okay.
But you know, it's not something you have to memorize because you can sort it out as you go.
No, I didn't even see where it said that. I was just trying to figure out
Okay.
just by based on thinking about it. That's why I asked that.
Okay. All right. Does anybody have any questions? Anybody have any questions about the test question? What they're going to see? So there's no real resource. I mean, there's no other practice problems because I'm telling you, you're getting one of these 6. So I'm just telling you should study these 6. Like I said, they are in the blue book as well. All right, any questions? Any other questions? Okay, well, let's get on to stereochemistry then. Now I've got a video here. Let me see. I think the share, let's have a look. No, it's fine. Okay.
So I do have a question about the favoring. It's not going to be for every single one. Like sometimes there's nothing that's favored.
Well, for 3 of them, nothing will be favored. For 3 of them, something will be.
How do you tell?
Well, let's go back. Let me go back to the PowerPoint here. I'll show you. So for the ones that have one axial and one equatorial methyl, there won't be a favored. Like
Got you, because of the count on them.
Right.
Okay.
Like cis 1,2, cis 1,4, and trans 1,3. Those will not have a favored one.
So you want them to be on the same?
Well, no. What I can tell you is that cis 1,3, trans 1,4, and trans 1,2 are going to have favored because you will have either both axial or both equatorial in those instances. To be not favored, you have to have one axial, one equatorial in both.
Okay, thank you.
All right, any other questions? Okay. All right, let's go back to, let's see, Introduction to Stereochemistry.
We'll introduce you to the concepts of chirality, stereoisomerism, and optical activity. Well, let's start off with chirality. An object is achiral if it is superimposable on its own mirror image. So we've got a pen here. This pen happens to be symmetric. So we take the mirror image of the pen, and you'll notice that when we take that mirror image and we lay it on top of the pen, they match, everything's okay. That's what superimposable or superposable means. An object is chiral if it is not superposable on its mirror image. So here's an example. You've got this car, it's got this red wheel on this side and a green wheel on this side. You'll notice it's not a symmetric car. Take a mirror image of that car, and then when you try and line them up, you'll find the wheels don't match. That is not superposable on its mirror image. This car would be chiral.
All right, so the point I'm trying to make there is that if you've got something that's symmetric, then it's going to have a superimposable mirror image. But if you've got something that's not symmetric, then it's not going to have a superimposable mirror image. The term chiral comes from, I think, the Latin, might be the Latin, that means hand. And the whole point is that if you've got two hands, unless your name is Mickey Mouse, then you can't lay one hand on top of the other and have everything match up. I don't think anybody's name here is Mickey Mouse. So when you try and lay one on top of the other, your thumb lines up with your little finger, etc. So your hands are actually mirror images of each other. They're chiral. And the same thing can apply to molecules as well, as you'll see in a second.
Now this applies to molecules as well. Now you'll notice that we have a molecule here that has two of the same thing attached to this carbon atom. So we've got two fluorines here. We take a mirror image of this molecule. Take a look at the mirror image. See how the green one here in the front, and here they are here.
Okay, is anybody having trouble figuring out that mirror image and how I've got that mirror image?
And you've got the blue one at the back, blue one at the back, red one front, red one at the front. So that's a mirror image of this compound. Now you'll notice in the next slide that what's going to happen is this is going to be able to be turned around and lined up. So exactly what we started with. They are exactly the same now.
I don't see that.
Now let's take a look at a with.
Okay, watch it again, Julie.
The problem is I can't hear it from your computer, and I don't know how I missed that one, but I didn't see that video yet, so I'll have to go back and watch
In
it.
the next slide, that what's going to happen is this is going to be able to be turned.
You can't hear it, Julie?
Now I can, but you
Okay.
turn it up.
All right.
Turned around and lined up, so it exactly matches what we started with.
Did you see how that twisted around and now they match up? So the red matches up with the red, the blue matches up with the blue, and the greens match up. Now this is achiral, which means that it's symmetric. So let's look at what happens if it's not, if it's chiral.
They are exactly the same now. Now let's take a look at a molecule that has 4 different things.
And this is important. The only way you can ever get a chiral molecule is if you have 4 different things attached to the carbon atom. You'll see why in a second.
Attached to the carbon atom. We take the mirror image of that. Now if we attempt to line these two up, look what happens. The reds and the purple ones, the bromine and the iodine, won't match. They won't match up.
Right, so the rule is if you've got 4 different things attached to a carbon, if you attempt to take a mirror image, you won't be able to take those molecules and line them up with each other. There's no way, there's no possible way, but you can make that happen. So that's what we mean by a chiral molecule. Now you might be wondering, you might be saying, well, gosh, why does it matter? Well, it does matter because there's lots of things, well, especially in the body. Most of our, well, pretty much all our amino acids, I think, are L amino acids. L means, L is one specific stereoisomer of the amino acid. And it's only L amino acids that will fit into certain enzymes. There are very few what we call D amino acids. Those are the opposite. Those are the opposite ones.
This is all a consequence of the fact we have 4 different things attached to this carbon atom, and when we take the mirror image, we find that we can't superimpose the mirror image on the original compound. That's what makes this molecule chiral.
So what if there's only 3 things attached?
2 structures.
Well, you're always going to have 4 things attached, always. What matters is if 2 are the same, Julie. If 2 are the same, 2 or more are the same, then it's never going to be chiral.
Okay.
You have to have 4 different things.
The original structure and its mirror image are called stereoisomers.
Yeah, so this is or enantiomers. Enantiomers is another term we use here. Stereoisomers or enantiomers. Enantiomer is the mirror image of a compound you initially have.
Stereoisomers have the same molecular formula but a different spatial arrangement of atoms. And here is an example of that. These 2 things will be called constitutional isomers because you can see that this is an ether and these are alcohol.
Okay, so an alcohol and an ether, those are just regular isomers that we're used to drawing. But these 2 here are stereoisomers. They're mirror images of each other that aren't superimposable.
An alcohol. But if you take a look at these 2 alcohols, there's F and CH3.
All right, now let's look at what makes them different.
Because you can't take this and line it up. Now we can actually, and the hydrogen.
I'm going to skip over the naming here. We're going to be doing that later, but we can actually name these differently, and I'll show you how to do that in a bit. Now, how would you tell the difference between them? Well, let's have a look.
Even know that these things exist, how do we differentiate between enantiomers? How can we tell that they're any different? So if we take these 2 compounds, which are enantiomers, I want you to look at this carbon here and be convinced that it's got 4 different things attached to it. It's got an OH, an H, a CH3, and a CH2CH3. And this is the mirror image of it, and that would be this would be considered a chiral compound. And this one is actually S. This one is R.
So I'm going to show you later how we determine the whole S and R thing, but it's got to do with orientation around that carbon. But we'll get to that. All you need to know at this point is that if one enantiomer is S, the other one's going to be called R.
R, based on what we were doing earlier. It turns out they have the same melting point, same boiling point, same density, same pKa. So they don't look very different. How can we tell them apart? Well, the only way we can really tell them apart is to see how they interact with plain polarized light. So this is a typical light, and a typical light will have light that travels in all directions. You can see that here, infinite number of planes. But if we put a slit in there, we can block out everything but one plane of light.
Yeah, so that's plain polarized light, when we block out all of the light except for one plane of it.
This is plain polarized light that we're looking at here. Now if we take one of these, we'll take the R isomer and we stick it into a tank and we put it inside this light beam, it will actually rotate that light beam.
So that's what these will do. They'll rotate the light beam. So R will rotate at 13.5 degrees. I guess it would be counterclockwise. The S one will rotate by exactly the same amount, but in the other direction,
due to its chiral nature. Now this particular one, the R isomer, will rotate plane polarized light minus 13.5 degrees. So 13.5 degrees in this direction right here to the left.
Now to the left means it would be what we consider an L compound if we're talking about optical activity. And if it's to the right, it would be called a D compound. L levo, D dextro.
Now imagine what happens if we put the S in the same beam of light. Now it rotates it in the opposite direction, positive 13.5 degrees, or to the right. So it's going to rotate plane polarized light the exact same number of degrees, but in the opposite direction.
Now, one thing I can tell you is the R and S is a completely artificial way of naming these and has no relationship to which way it twists plane polarized light. So you can't always say, well, R is always going to be positive and S is always going to be negative, or vice versa. It's always going to vary because it doesn't matter.
Now the other one that went minus is called a minus or L compound, and a molecule that rotates light clockwise is labeled a plus or D compound. You might have heard of dextro-rotatory and levo-rotatory. D is for dextro, it means to the right. Levo-rotatory, that was minus, and that was to the left.
All right, so that's pretty much everything about optical activity that I wanted to talk about there.
But there's no relationship really.
Yes, I already said that. Let me get out of here. Okay. Did anybody have any questions at this point? So these are the terms that we're going to be talking about here. A chiral center is a carbon with 4 different groups attached to it, because in order for something to be chiral, we need 4 different things attached. Absolute configuration, that's whether it's going to be R or S, and I'll show you how to get R or S in a bit. Now, plus or minus is a bit different. That's the direction it twists plane polarized light. If a compound is optically active, it produces rotation of plane polarized light. And an enantiomer is the mirror image or partner compound of opposite configuration. So if you have R, the enantiomer would be S. A diastereomer is a compound that results from switching some but not all chiral centers, and we'll get onto that as well. A racemic mixture is a mixture containing equal amounts of R and S. And because they contain equal amounts of R and S, they're optically inactive. So if you have a 50% R, 50% S solution, the like plane polarized light doesn't know which way to go, so it just doesn't do anything, just goes straight through. So technically it is a chiral mixture, but because you've got R and S in equal amounts, then it doesn't twist plane polarized light at all. That's what racemic means. And a meso compound is a compound that contains 2 or more chiral centers, but it's optically inactive because it's got an internal mirror plane. So I'll show you examples of those as well. It's kind of like a racemic mixture is 2 different compounds. A meso is like sort of the same the same compound, but it's got chiral centers, but it's not optically active. All right, but we will get into all this terminology as we go here. So this is an example of how to assign stereochemistry, how to assign that R and S that I talked about. And it all comes back to that same rule that we talked about when we were doing the E and Z nomenclature, and we were talking about the priorities. And we do the priorities exactly the same way as we do the priorities with the E and Z. Now, when we do this, what this all depends upon is the ability to be able to put the lowest priority group in the back. So if you've got this compound here, which has a C that's got an OH, an H, a CH3, and an NH2, those are the 4 groups that we're talking about, then we can prioritize them on the basis of their their atomic weight, like we did with the E and Z. So the number 1 priority would be O, then N, then C, and the lowest priority would be the H here. Now the H here has to be in the back. Now you remember what I said about the wedges and dashes. If something has a wedge on it, it's coming out of the page. If something has a dash on it, it's going into the page. It's the one that's got the dash on it that goes into the back. Now I'm going to go get I think I've got my models here. I'm going to get a model and I'll show you how that rotation works. Okay, so I've got a carbon here. I'm going to put 4 different things on it. I'll put a blue for the nitrogen. I'll put a red for the oxygen. I'll put a yellow for the hydrogen. And I'll put a black for the carbon here. Now let me make sure that I've got this lined up in the same way as this one is. Have I? No, I haven't. I'll switch these 2. Had a 50-50 shot. I lost my oxygen. That's dangerous, isn't it? Losing one's oxygen. Okay. So here's the molecule. Now presently, you'll notice that that's the thing with Zoom. It always makes, this is difficult. Zoom always makes the mirror image of something. All right, let's do this. Okay, I'll put the hydrogen, here we go. So I've got it set up so that let's see if I can do this. All right, there we go. This is difficult. All right. It's difficult because Zoom gives you a mirror image of something. So it's a tough medium through which to do stereochemistry. All right, so I've got the hydrogen here at the back, and what I need to do, sorry, I've got the hydrogen here. I'll put it towards the front, and I need to put this hydrogen towards the back. The way I'm going to do that is I'm going to rotate it. And that puts the hydrogen at the back. So that's what I'm doing in the diagram. And this is what I did here. I left this CC bond the same, and then I just rotated it like an airplane propeller. By doing that, I'm not changing the compound. All I'm doing is putting the hydrogen at the back, and then I look at the order of the 1, 2, and 3, whether it goes clockwise or counterclockwise. If it goes clockwise, it's called R. R for rectus, meaning right. And if it goes counterclockwise, then it would be S for sinister. How many left-handed people do we have? Any left-handers? Any left-handers around? No, no left-handers. Okay. Left-handers were called sinister because there was something thought to be evil about left-handed people. But that's where the S comes from, sinister. But this would be R that we've got here because we have to put the lowest priority group into the back by rotating it and then look at the 1, 2, 3, whether it goes clockwise or counterclockwise. So it's called R1 amino ethanol, but it's the R that we're most interested in here. Does anybody have any questions? All right, well, that's about all we'll do today, and we'll get really into the stereochemistry in the next class next Monday. In the meantime, I'd recommend watching those stereochemistry videos. They're actually pretty decent.
Thank you.
Thank you.
Okay, no worries. I'll see you all later. Some of you I'll see you in lab.
See you in a bit.
Yeah.
Bye.
In a bit.
Musgrave, I have a question.
Yeah.
For the lab, what is the last day worksheet? I know that's like far off in like terms, but I was like wondering.
It is actually counted as a lab, but if you've done all the labs up to that point and you're happy with your grade, that's the one that gets dropped.
Oh, okay, perfect. Because as you know, I'm like working ahead.
Oh yeah. Well, you know,
Yeah.
if you get them all done and you get more than 90% on them,
Yeah.
you won't have to do that.
Yeah.
You won't have to do that last day worksheet.
Okay, that sounds good. Because I was like wondering what it would be. So, yeah.
All right.
All right. Well, see ya Monday, I guess.
Okay. See you, Courtney. Bye.
Bye.